So this is the second part of our presentation. So good data collection is essential because then we can see how these the locations of the accumulation of these earthquakes and also the gaps in these accumulations, because this will carry on along the fault. So good data collection is very important for this type of investigation. And there was a similar situation for our North Anatolian fault. And it's like, because when one part of the fault slips, this slippage releases the energy at one part and then accumulates the stress on the part of the fault ahead. When that part breaks, it moves, but then this movement causes the accumulation of the stress in the further part. So we know that it's going to happen. That's where the stress is transferred. We don't know when it's going to happen, but we know that it will happen. And when it does happen, how much magnitude it will produce, we know that. So we can design accordingly to that. Okay. So I will keep on coming back to this over and over again. This is not an issue that we can gamble with. This is not an issue whether we can say that, hey, maybe our structure maybe will not see this. You know, its service life is 50 years. Maybe in this 50 years, it won't see the earthquake, so I don't have to do it. This is a very ugly discussion in my point of view, because yes, as a structure, it does have a cost, an engineering cost, but you know, as civil engineers, we should be mindful of the fact that when our structures are there to serve a purpose, so the people who will live in our structures, the people who will use our structures, the amount of added value. I mean, if we really want to speak in terms of costs and money, if we as humans only can understand costs and money, let's do so. The amount of added value that a human will generate in that structure is much higher than the cost of that structure. Think about one family, a family flourishing in a house, and the amount of added value that they will produce as they work. This is humongous. Or like, let's talk about a factory, right? The cost of the factory building and the cost of the product that will come out of that factory. So these are something that cannot be compared. So I, for example, as a civil engineer, I always support this notion. Make it stronger than it needs to be. So what? Because the amount of destruction that happens at the end is not worth it, simply. And also there are some, I mean, I wish I had more room today to discuss about that too, but for example, performance-based criteria. At the event of an earthquake, the building will not fall down, but it will, be damaged. What does that mean? Like, have we seen a picture of that? That would mean walls that have cracked. That would mean shear walls that have cracked. That would mean a structure that one cannot live in. Yes, I'm alive, but I'm bankrupt now, because owning a house isn't an easy matter either. So the way this construction industry goes hand in hand with politics is a very, very dangerous thing. The structures should be designed actually to respond elastically to even the high loads. That's my point of view. Yes, it is an expensive point of view, but this is, I think, the safest point of view, because the other ideology is quite dangerous, I would say, to play around with. This is my point of view on this matter. There are some similarities between the fault behaviors between Turkey and California, for example. They are both strike-slip type of faults. And the way they behave, the way they function, the way they evolve are quite similar. So in terms of examples, we have good examples to compare ourselves to. Tectonic motion, of course, surveying is a very important field in civil engineering. And for especially seismological purposes, surveying is very important. And they use the methods of triangulation, lateral and vertical positioning to do so. And today it's a very important field, I would say, especially when the increasing populations and the accumulation of those populations on the face of the earth. Because the thing is, like, those tectonic regions created cities of today that are within or very near water lines. or within certain advantageous positions, geographical advantageous positions, but actually those advantages are caused by earthquakes. So there's like this interesting correlation there. In the middle of nowhere is nobody's business, but yet it is seismically safe. But in a city that is at the mouth of an ocean or at the like the Bosporus, it is very easy for transportation purposes, and that's where people accumulate. That's where the highest populations are densified, and yet those are the regions where dangerous earthquakes are happening. And the population of the earth is increasing. There is a strong conveyal of people from the rural areas to the cities. So this resistance against earthquake is becoming more and more important every time. And of course, the only way to construct against earthquakes is not to resist against the forces, but isolate yourself from those forces. So the seismic tectonic motions could happen, but by using seismic isolation, we can isolate ourselves from that effect. But nevertheless, we need to make safe and habitable structures in the face of adversities as well. This is my point of view. So I would like to pass on these slides for the volcanic earthquakes, subsidence earthquakes, hydraulic earthquakes, explosive earthquakes. There are other generators of plate motion. And I'd like to talk more about elements of structures. Now, what is a structure? If I were to start with that definition, it is a formation of solids with designed geometric and material properties. It's a formation of solids, and we define the geometry and we define the material of that solid. And it's designed to provide a geometric location to a function within space. Like I am right now in my working room. I am 19 floors above the ground. I am about 60 meters above the ground. So all these walls around me is meant to keep me 60 meters above the ground. If for some reason I find myself at the ground floor, something bad must have happened. So that is the function of this structure. And it is designed to respond to expected loadings within functionality and safety limits. This is my definition of a structure. So the limits are imposed by the functionality of the materials that the structure is composed of and the conditions of use that the structure will be subjected to. It must be stable. A stable structure must be strong enough to resist loads and stiff enough to resist large displacement. This is the quality of a structure. So when we think about it, like how can we act in a structure? What can we do to a structure? When I think about it, I came up with 5 different types of actions. We can pull it, push it, shear it, bend it, or twist it, or a combination of these 5. Okay. So actually in our classical mechanical world, we can put the boundary. So we need to design for 5 different types of actions. So for example, what is this? This is a composure of 3 beams. And I imagined this as a diving platform for a pool. So this is supported at D and the load is applied at A. So what's going to happen? What is a structure? Well, the structure is meant to provide this position for this arrow, the loading value. And the force at point A, just the force at point A, generates a shear and a moment at point B. But this shear and this moment at point B generates a shear, a moment, and a torsion at point C. And the shear, moment, at torsion at point C generates biaxial bending, 2 moments at the base D, and an axial force. So this is a load path, taking this simple load that has manifested itself as 2 bending actions and 1 axial action at point D. We can talk about this for any type of structure, but what makes this structure a structure is its connection. Because if this connection at point D is not capable of dealing with this, what this happens, it's not even a structure. It is just basically this odd shape of mass. That's it. It is not a structure. This is a structure as long as AB can bend, as long as CB can bend and torsion, as long as CD can bend. This is a structure as long as it can manifest these behaviors. And what is forcing them to manifest that behavior is the support condition at point D. So the structure is defined by its support, and it's as strong as its support. So why am I highlighting this? Because in prefabrication, this is the most fundamental aspect of it, the support itself. You have to explicitly define and understand what will happen at the support and design it accordingly. the design of this, okay, the element is important, yes, but this is nothing but a load path. This is a highway for stresses, taking the load from one point, transferring it to another. If this path is broken, no structure. And this, what makes this a structure is this support point at point D. Supports are very important. The continuity between structural elements means the ability to transfer the selected forces from one element to the other. A structure requires a state of stability such that for every imposed action can be reacted upon. Okay, for every imposed action need to be reacted upon. And stability cannot be achieved if the reaction to the imposed loadings cannot be developed at the support points of the structure. And a structure is the union of structural elements and joints, and a structural element can be only as strong as its joints. During the design of a structural element for an array of forces, one is assuming that the required reactions will be provided by the joints of the structure. The joints are assumed to be properly designed, so we need to make sure that they actually are. Because sometimes the damage that we observe is not due to the structure element in and of itself, but its location of support. So this is important. So the design of a joint or a support requires a thorough understanding of the balance of forces at the joints. A designer must be able to visualize the structural action within the structural element or joint prior to the design of the structure, and then configure the load path within the structure that provides a stable link between the point of action and the point of reaction. So when we talk about prefabricated structures, whether it's steel or concrete or cast in place or prefabricated, the notion is always the same. What I think distinguishes prefabricated structure from the others is that all the locations of support are explicitly defined or explicitly seen. So this provides a benefit in that sense. If there's shear, you ask the question, how am I going to respond to that shear? If there is a moment, you ask yourself the question, how am I going to respond to the moment? So you can define it explicitly. Nothing is buried under concrete, under the free-flowing concrete. Everything has to be responded to. But if it's not responded to, right, then it will fail from the joint. Sometimes in the earthquakes, there are pictures of prefabricated structures where the elements are all over the place. And then, of course, economy and politics is entering everything. And then sometimes there used to be some negative propaganda saying that, oh, prefabrication is very bad for design. And who was saying that? Either the cast-in-place people or the steel people or whatever. No. If the structural joints is not properly designed, everything will fail. Okay? So this is not a matter of, being a fanatic of one type of material over the other or one type of method of production over the other. Everything has its place in an economical and a correct form of thinking. But what I would like to say again is that the structure is as strong as its connection. This is what I would like to highlight. And sometimes, on the paper, when we could do a simple beam to column connection, we show it like a simple dot or a simple triangle or a simple roller, simple. Here you have a connection of a girder with a column. This is the dot. This big chunk of element is the dot. So the state of multi-axial state of stresses in this region is tremendous. And how well this frame will function is basically related to how well this connection will function. This is what we typically have. This is a depth and beam sitting on a corbel of a column, and it's topped by precast flooring. So depending on what you want to achieve, if you want to achieve a simply supported action or a moment connection, there are different types of connections, depending on how much pulling action is going to be, how much pushing action is going to be, the number of bars protruding away, and the number of anchorages are determined. These are all tested, by the way. These are all verified that if done right, it does function right. But this, for example, does not provide any moment transfer because there's nothing providing the axial forces at the top edges, only shear. So this is simple support. So we need to visualize the stresses for the bending, for the shear, and for the torsion, and respond to it in an appropriate way. We have the tensional stresses, the compressional stresses, the shear stresses, and every single one of them, for example, when we are designing this corbel, the shear that is transferred, it flows in and into the column. And then there's a big, interesting anchorage design at this portion to provide that path for it, okay? So the good thing is that we can clearly visualize, see it. Nothing is covered, nothing is buried over here. Every single one of them is designed separately and connected in an explicit way. For example, torsion. Torsion is a type of bending generating shear stresses, and it is a very critical element. And if overlooked, creates extreme amount of damage, okay? So we need to have that understanding, and prefabricated design also allows us to deal with this type of stress as well. So the strength values of materials, of course, the geometry and the strength. So what was the structure is a mixture of the material qualities and the geometric properties. And as an engineer, we select our material and design a structural element such that at any point along the structure, the level of stress and the level of deformation is engineered to an acceptable value. So when we design something, we are saying this: I have developed a formation of material at this geometry, and I know how it will react when the loads are applied on top of it. I will know its reactions, how much it will deflect, if it will crack, or when it will crack. This is what designing something means. I can basically describe you its behavior all throughout its life in relation to the stresses that it's exposed to. Some materials are non-isotropic, some are not. They have different strength levels for the axial forces under tension, under compression, under yield, bending. So we need to know these limits. For example, when we deal with concrete, it has a different strength level at the compression end, it has a different strength level at the tension end, it has a different strength level at the shear. So whatever I do, whatever is generated there, it must be within this. So then, of course, comes the more circles. It's quite useful. It's very useful. So it is something that one needs to have a full grasp of, because, every material has, like, for different types of actions, it has different types of reactions, or if different types of mechanical capabilities. So you have like 3 or 4 racehorses, okay, but they are not all the same strength. One of them is stronger than the other. For concrete, it's compression. For steel, it depends. So there are all these issues that we need to understand and appreciate about the material that we use. The multi-axial state of stresses, which happens at these connections, can shift the failure pattern, depending on the types of, when we apply a force on one direction, it doesn't mean that it's not going to respond in the other direction. Poisson's ratio, for example, the fundamental relationship. So by manipulating the amount of confinement that we have, we can actually extract more strength from our design just by the manipulation of contractions. So it's a beautiful thing. Structural design in this sense is a beautiful thing. By manipulating the way it responds, you can manifest a higher strength from that. For example, if we are talking about an axial compression stage, well, if it's unconfined, it will have one strength. If it's confined, it will have a different level of strength. And of course, for example, perhaps the simplest that we want to know, that if, when we do a concrete cube test, of course, from the platens, we have this confinement issue. So depending on that, actually, when we release it, we get a much smaller stress of breakage. But when this confinement is high, we can expand it. So what is that doing to us? What it's doing, it is basically closing our Mohr circle. So it's not touching this limit of failure under shear, this 0.12. So these are, I worked on some numbers based on the Poisson's ratio and the concrete and the coefficient of friction between concrete. Once we have that platen, it basically pushes this Mohr circle, makes it smaller and smaller and smaller. So it's moving away from the limit of failure under shear. Coming back to our corbels, again, this was at one point, it was a very wide field of research, especially Precast Concrete Institute in the United States in the early 2000s. So it has some beautiful, interesting details in this. So how this load is received and how it's directly transferred to the steel. There is some very good details here where the loads are taken by a steel plate, which is welded to the steel rebar and then anchored with it. So then it functions well. It does function well. But the type of stresses, the tensile and the compression stresses that occur here, is far beyond, you know, when we refer to it as a simple point connection. It is more than that, much more than that. Or the depth and beam. Like, look at this now. So we have stress fields, right? So we have the tensile field, we have the compression fields. So what is this? It's actually a nuisance. This is not doing anything. And yet, you know, when we put this like, when we hang it, right? The potential areas of breakage is something that we need to stitch through. So what is reinforced concrete design, right? It is, we are stitching basically. In reinforced concrete design, we need to understand about how it's going to crack, determine those locations and stitch through it. That's what we do in reinforced concrete design, okay? And the more we allow ease of flow of stresses, the better it is for us, because whenever flow is confined, that's where stress concentrations happen. And that's when our design is compromised. We have to be careful on that. So there's a bunch of details for, I'm showing here the simply supported cases, but it does work. It does work beautifully, and it does work explicitly. So if understood right, if applied right, if constructed right, prefabrication has a lot of solutions to some of the problems that we are facing today. Well, what about moment connections? Well, what about moment connections? Well, if you have the moment, then you need to have a force couple. Then you have to provide something to the above. You have to provide as a form of anchorage that connects everything, a steel structure. And we have that. We have special details for that to provide that moment connection. So when I want to bend this beam, I have the force at the bottom, force at the top. If it's reversed, tension and compression, force couples, it can work, it does work. But we need to respond to it explicitly. That's the important part. And then we have the columns. A typical design for the cast in place, we have a similar design for the prefabricated version, where the column is socketed in a socket that can be also prefabricated, which is designed according to the geotechnical conditions, and then the whole building from the ground up can be actually prefabricated. So all these elements can be responded to in detail. So having said all this, what I would like to come is to a more particular detail, the ductility, the concept of ductility. And I would like to discuss certain things. When we, for example, look at the tables, for example, S220 steel, it yields at 220, S420, it yields at 420, and then it fails, the maximum stress that it can reach is 340 for the 220 and 500 for 420, so on and so forth. And I would like to have a question to the dear students. I want to ask you something. When you design with steel for reinforced concrete or for steel, which stress value do you use? You can open up the microphones, please, and respond accordingly, please. Which stress value do we use as our mechanical design parameter?
So you mean the strength value?
Yeah, when we design, right, like rebar, which material strength value do we take, and when we multiply it with the material constant and so on and so on?
Tensile strength of the steel.
Yield strain, you mean, right?
Yield
strain.
yes.
So
yield.
we don't want the material to yield. We take the yield strain and then we multiply it by some constant lower than 1, and that becomes our design value. Am I correct?
Yes.
Am I correct? Does everybody agree in the audience, please?
I am agree too.
Okay. So this is what we are after, right? The minimum yield stress value. But in this table, a lot of things are given to us. You know, the minimum tensile strain, ultimate tensile strain value must be 18%, 12%. Why do I need them? Why are they important to me? I don't use them. I mean, even in the seismic forces, right? I design to resist those seismic forces as a certain percentage of my yield stress. Why do I need them? Why is this table telling me it must be 18%? Why is this important?
Because we design in a plastic zone. So we accept the yielding, and we need to know how much elongation we have in yielding zone. before
But
the
this is
collapse.
tensile strength. It is way beyond yielding. Why do I care if it's 18%, 19%, 21%? Why do I need this? Why is this significant? Is it significant? Well, it's asking for it. Or for example, when I have an itch dash, for example, test my specimen. So it is giving me a chemical analysis, a carbon equivalency test. These are all important. It is unit weight and minimum yield stress value and maximum strength, tensile strength. Here we go again. Maximum tensile strain. Why do I need this? Why is this important? I'm not using it. This is what I'm using, not this. I'm using this one. And I'm using only a certain percentage of this one, like maybe 70%, 65%, whatever, right? So if this is 47, I'm using 30 something, 300 megapascal, something like that. Then why? So this is a 420 steel, by the way.
Because in the seismic load, we have to understand the capacity of it, like how much the strain is going to happen.
Why?
Maybe.
High performance design. Some people want to do high performance design.
Those are very complicated words for me. What does high performance design mean? I mean, did I say anything in this presentation that confused you? Any words that came out of my mouth that confused you? Now you confuse me. High performance design. What does that mean?
Isn't that the design that you mentioned in terms of some people doing like structures that will break, crack, but not fail?
No, load and resistance factor design. No, I'm not talking about that type of plastic. So let me just come to that, what I'm talking about. Here we go. S220, 420. So this is where you are working. This little zone is where we are working, elastic zone, right? And then there's a strain, this plateau, yield plateau, and then this is the strain hardening region. I mean, we are working all the plastic stuff, everything, all this fun, good stuff is happening in this region, maybe slightly ahead. Why am I dealing with this part?
Because in the earthquake or seismic loads, it's gonna fail, maybe. If it's fail, we have to know how much flexibility we have or how much yielding we have. I think it's important part. Before the failure, how much it's gonna yield, maybe.
But I mean, in design, your seismic forces, you estimate your seismic forces, and then you calculate your rebar requirements again by these values. So even on the seismic loads, you don't design your structure to go all the way to this region. You design it so that it will happen here.
Yes.
So what is more than gonna what is bigger than the seismic forces in this case? What else is gonna happen to the structure to have me go all to this part? Now, by the way, mind you, the elastic stress strain is 0.1% for S220, 0.2% for S420. Okay, the plateau is 1.1% for S220, 0.8% for S420, and then this part is 16% for S20, 10% for 420. So that we have our, so this is about like a big time larger than this, quite a lot, like 16 times higher, 10 times higher. So let's think like that. Why do I need?
So we have the yield strength of elements, but we have too much elements in a structure. So if an element reach its yield strength, this means this element cannot carry more load, but it can continue to elongate. So the stress distributes other elements. So this strain value means ductility, of course. So we can predict the ductility of the structure from these values. So,
okay, I agree. But then let me ask you this. At what part of your design have you ever used 5% steel elongation in your design, in your calculations? Have you?
the R value of the in the seismic codes, am I wrong? We take the ductility value and we divide the force from the seismic movement. So we use this.
So the R value, is the
Ductility.
R value only related to the material, nothing with the design? The R value has to do with the type of the, like shear
Yes,
wall has a
yes,
different R value,
yes.
reinforced concrete design has a different
The
R
R
value.
value is the ductility of the system, basically, but the ductility of the systems, the materials and the structural system affects the whole ductility, of course. So if there is only simply supported beams and columns in reinforced concrete, this is a different ductility, but it's only a steel building, like a moment frame. So it's another ductility. It differs. It
So I
depends
agree.
on
So
material.
when we take our seismic forces and divide it by 8, for example, our R value, and design for 1/8 the value at this point, if the earthquake hits, it is going to force this all the way in this region, right? And then
Yes.
this is a part of our ductility. That could be a part of the question. And of course, the R value is not a sole quality of just the reinforcement, but how the structure is composed of, right? That's also related to that. And of course, when you are now in this region, your structure is not as before. It has deflected tremendously, right? I mean, let's talk about the 16%. So whatever you have is increasing in height of 16%. Do we think that, you know, if we go into this region, the shape of the structure will be the same as what we originally have if we are straining these elements that much?
No, but the main idea is not the not this. Main idea is to not kill the people. So we can demolish the building after the earthquake as long as there is no casualties. So this is the main idea of our design. Am I wrong?
Well, that is a part of the philosophy, certainly. But for example, for an R value of 8, if the earthquake that is 8 times what it is designed for acts on the structure, do we exactly know where it is going to be? Because this is a very nonlinear part. And can we just multiply? So can we say that, okay, we're going to be somewhere over here? Is it for sure? Or will I be able to hold on to these rebars to elongate them this much up to that point? Or can we,
I don't think
leaving the, okay, but I agree with that R value and the ductility and the energy absorbing capacity that you are referring to. I agreed with that. But is it the only way we do plastic design? Just this part? Like, is there any plastic design only for serviceability conditions? When you think about a
no.
reinforced concrete cage,
Yes,
how?
we define plastic hinges to the plastic hinges occurs
No,
in the
that's not what
case
I
of
said. That's not what that was not my question. Like in the normal ordinary concrete design, even for even for the service loads, do we do a plastic design? Is that yes or no? Just as when we do the design,
no,
no.
I
Okay.
don't think so.
So let's carry on, and then we'll give a break and then come back one more time. So this is my sketch. This was when I was just looking at different ductility characters of different grades of steel. As we increase the strength, the yield plateau is actually diminished like a triangled one version, like a triangled fashion. So just between S220 and S420, this is what happens, the plateau. This is about 10 times the yield. This is about 4 times the yield. So this plateau closes up. And then for high strength steel, we have a long elastic region, but then an abrupt fracture and brittle behavior commences, right? So our design material is mostly in this region. But when we think about this, what type of a design does this require? What is this? Is it an elastic
Yes.
design or a plastic design? When you bend the rebar, is it an elastic design or a plastic design?
Plastic.
Plastic. Because if it was to behave elastically, you cannot bend the rebar. In order to bend the rebar, we have to make plastic design. Am I correct? So just to set up your ordinary reinforced concrete reinforcement cage, we have to do a heavy plastic design. Is that so? I'm going to turn off again and then come back, but there's a lot of room to discuss over here, and this will be the final section of my discussion, okay? So let's end it here. Let's come right back